Welcome, and this is my presentation on vasoconstriction and thermoregulation. So what is thermoregulation? This is the natural process within the body that allows it to maintain temperature homeostasis. Some examples might be sweating and shivering. These are also forms of vasoconstriction and vasodilation. In this presentation, I'll be going into a little bit more in depth about vasoconstriction. So this is what happens when an organism is exposed to cold temperatures, and it's the process where one's arteries constrict to keep blood more circulated internally to keep one's organs warm. This is an example of a normal artery and a constricted artery right next to it. This is all pretty simple, right? How does this process start? It's common belief that this is how the vasoconstriction process works. Body enters a cold climate, arteries constrict, blood flow circulates around the body, organs receive most of the blood, and this is a negative feedback loop that will continue to go on until the body is exposed to either a warmer climate or it runs out of energy, in which case you have to be concerned for cell death and the health of the organism. Now, what if I told you otherwise? What if I told you that the skin probably plays a much bigger part in temperature regulation? So Romanovsky hypothesized that skin actually acts as a feed-forward control for the rest of the body to kind of continue this process of vasoconstriction. Well, here's the evidence. Yusuf conducted an experiment where blood flow in volunteers' fingertips underwent CIVC, which is cold-induced vasoconstriction, by submerging the volunteers' fingers in cold water. When measuring the blood flow in these patients' fingers, Yusuf came to the realization that vasoconstriction was induced not when the internal body temperature was kept warm, but when a certain amount of heat had actually dissipated from the skin. So, for example, this is me, roughly 2 years ago, standing out in the cold with no protective gear. My arms and legs are losing heat. The skin temperatures are sending signals to my brain, and then my brain is inducing vasoconstriction. So now what's happening on a more biological aspect? Well, GABA is a neurotransmitter responsible for calming the body after long stressful neurotransmitter releases. So this will be released after the entire vasoconstriction process is done. Nakamura and Morrison electrostimulated anesthetized rats to see what would induce shivering. Shivering was not present in these rats unless GABA inhibiting chemicals were introduced to the rat. That was when the body was able to shiver. So that implies that GABA itself has this way of calming the body when it's released and therefore prevents shivering. Now, T subscript 8 represents temperature, and TRPM8 was studied to found to be the protein channel that is active throughout this process of vasoconstriction. In an experiment done by Gavin and Davis, TRPM8 agonists were introduced and noticed that there was no change in temperature levels, implying that when they are there and those protein channels are open, the body is able to regulate the temperature more easily. So now what about oxygen distribution? Because that's important to keep cells alive. So through implemented temperature loggers, Cadena and Tattersall were able to log oxygen distribution in rats exposed to cold, hypoxia-inducing states. That's when there's not enough oxygen and the cells begin to die. Results from the study show that oxygen actually has a steady decline when first exposed to colder climates. That's why, for example, if you were climbing a mountain, you would find yourself shortness of breath the higher you go. But then after you would stay up on said mountain, your body temperature and your oxygen levels would begin to stabilize as it gets acclimated to that environment. As was shown within the study, the body temperature and oxygen levels stabilized after a couple hours and reached average hypoxia-inducing states. So the takeaway is that oxygen is actually being consistently circulated throughout the body when exposed to frigid temperatures, and this is known as the Hunter's reaction. So an overall summary: skin senses the cold, it sends effort messages to the brain opens TRPM8 proteins and inhibits GABA release, the body shivers, oxygen circulates, and it will do this until the body either runs out of energy or it gets put into a warmer climate in which GABA would be released, and it would start this relaxation process. These are the basics, right? Well, there are some theories that suggest otherwise. Kenny Segal and McGinn hypothesized that patients with type 1 and type 2 diabetes have trouble regulating their peripheral vasoconstriction system. However, there's not enough evidence to support this hypothesis. More studies need to be done, and as of right now, it is just belief that it is an issue of glycemic control.